Hello everyone. One of you suggested a video about retrosynthesis, and here you go.
In this video, I'll show you how to analyze target molecules and how to come up with reasonable proposals for their synthesis.
At the beginning, I'll discuss some basic concepts, and at the end, there will be some practical examples.
The goal of retrosynthetic analysis is to find the safest, least expensive, environmentally friendliest, and shortest synthesis for a given target compound.
The optimal synthesis depends, however, on its scale and on the purpose of the synthesis.
A compound described in patents or a journal may, for instance, be required for biochemical or pharmacological research as a reference compound on a small scale, typically less than 100 grams.
In medicinal chemistry, often many related analogs of a given lead structure are required, also on a small scale.
In such instances, the chemist faces less stringent limitations than in large-scale, batch-wise, or continuous production.
So, if you have to prepare a compound on a small scale, I would just use the literature procedure, because the main goal is to get your hands on the compound as quickly as possible.
The price of starting materials and reagents, waste disposal, safety, and potential corrosion of equipment are irrelevant here and do not need to be considered. Safety is of course always important, and you should have an idea about the toxicity of reagents and intermediates and about fire and explosion hazards.
But the smaller the scale of a reaction, the less critical these issues become.
If you have to prepare many analogs of a lead structure on a small scale, the synthesis must be reliable, easy to perform, and flexible for structural variations. Ideally, it should be based on readily available starting materials, for instance, alcohols, amines, or carboxylic acids, which are stable and on hand in large numbers. Again, the overall costs, waste disposal, safety, and corrosion are not critical at this stage. The commercial production of compounds on a larger scale is, however, a different story. Here, the synthesis must be optimized, and the costs of starting materials, reagents, solvents, and waste disposal are critically important, as are safety and equipment corrosion. If less than 50 tons are required per year, such syntheses are usually conducted batch-wise in a multi-purpose plant. But in recent years, continuous processes are sometimes developed, even for pharmaceutical or agrochemical intermediates. One advantage of continuous syntheses is that highly reactive, toxic, or explosive intermediates are easier to handle safely than batch-wise. Exothermic reactions are easier to control, too, if the synthesis is run continuously.
Commodities are always manufactured continuously in dedicated plants.
Here, the chemistry must be optimized a lot, and all parameters must be carefully assessed. These include the availability of starting materials, the overall costs of plant construction and operation, the geographic location of the plant, waste disposal, corrosion, energy use, and safety. Synthesis and retrosynthesis are a bit like differentiating and integrating in mathematics. A synthetic reaction yields only one product, but a retrosynthesis yields many potential approaches, and you can never be sure to have found the best one. Retrosynthesis is also similar to chess and involves a lot of pattern recognition. As chemists get more experience over the years, we become better at recognizing characteristic structural elements accessible by certain reactions. But chemists should also be able to estimate boiling and melting points, solubility, reactivity, and toxicity of compounds.
Boiling and melting points are important for the isolation and purification of products.
Typically, organic synthetic reactions are worked up by pouring them into water, extracting the product with a solvent, drying and concentrating the extract, and purifying the product by distillation or crystallization.
Some products are volatile or tend to sublime and require low boiling solvents for their extraction.
High melting points often correlate with low solubility, and extraction with a solvent may not be possible.
Compounds with high melting points and low solubility also tend to precipitate as fine powders that can be difficult or impossible to filter off.
In such instances, the product should be crystallized from a better solvent, for example DMF or DMSO, or at a high temperature.
So, what compounds tend to have high melting points and low solubility in organic solvents?
Usually, the larger the molecule, the lower its solubility. Then, compounds that form intermolecular hydrogen bonds, for instance carboxylic acids or amides, also tend to behave like larger molecules. The number of freely rotatable bonds often correlates positively with solubility. And salts or amino acids are difficult to dissolve in apolar organic solvents. Terephthalic acid, for instance, melts at 427 degrees Celsius, much higher than benzoic acid, which melts at 122 degrees Celsius. This high melting point is caused by the hydrogen bonds between molecules, which give it some polymer character. Accordingly, its solubility is low, even in water or DMF. Thus, terephthalic acid cannot be extracted and must be isolated by crystallization and filtration. Esters of this diacid melt at a much lower temperature and are soluble in most organic solvents. Large symmetric molecules, for instance organic pigments like the one shown here, also tend to have high melting points and low solubilities. Pigment violet melts at 385 degrees Celsius and is virtually insoluble in any solvent. Such products precipitate directly from the reaction mixture, and the solvent, concentration, and reaction temperature must be chosen so that the resulting particle size enables filtration, and the resulting product is as pure as possible. Occasionally, solvent mixtures may be the most convenient option. Mixtures of dichloromethane and methanol, for instance, can be surprisingly good solvents for certain compounds. Amino acids are internal ammonium carboxylates and have high melting points and low solubilities, even in protic solvents. Therefore, these compounds are usually protected either as esters or as carbamates, which are much easier to handle than the free amino acid. Here are some further examples of poorly soluble compounds, including some organic pigments. Not only their isolation and purification, but also purity determination and their use as starting material can be quite challenging. When designing a synthesis, we should have a notion about the stability and toxicity of intermediates. Highly electron-rich or electron-deficient compounds will react with even weak electrophiles or nucleophiles, including oxygen, carbon dioxide, water, and proteins. Enamines, for instance, turn yellow or brown when exposed to oxygen, and tetraaminoethylenes even glow in the dark. Then, organic compounds with many weak bonds are reactive and sometimes explosive. Particularly reactive are allylic and benzylic halides, haloketones, epoxides, and compounds with nitrogen-nitrogen, nitrogen-oxygen, and nitrogen-halogen bonds. Other reactive electrophiles include acyl halides, anhydrides, and isocyanates. Strained rings like cyclopropanes or cyclobutanes and sterically crowded molecules can also be thermally unstable and reactive. Chemical reactivity often correlates with acute toxicity, and volatile electrophiles are particularly dangerous. If we compare the toxicity of electron-deficient alkenes, we see an almost perfect correlation between chemical reactivity and toxicity. Vinyl ketones and acrylates are the most reactive and the most toxic, while substituents at the beta position strongly decrease reactivity and toxicity. When analyzing target molecules, one obvious bond to cleave retrosynthetically are heteroatom carbon bonds. These are often easy to prepare by nucleophilic substitutions, reductive alkylations, or by reduction of amides or esters. Less obvious are retromichael additions, but these can be valuable carbon-carbon bond-forming strategies. Michael additions are less reversible than aldol additions, and the products are therefore more stable. Aldol additions and condensations, and their many variations, are among the most important CC bond-forming reactions in organic synthesis, and most alpha-beta unsaturated esters, ketones, aldehydes, nitriles, or nitroalkanes can be prepared by such condensation reactions. Many cyclic compounds can be prepared by well-established cycloadditions or cyclizations. Cyclopropanes, for instance, are obtained by addition of carbenes to alkenes or by cyclization. Beta-lactams are also formed by cycloaddition, as are many 5-membered heteroarenes. The quick recognition of retrosynthetic pathways requires practice, just like learning chess or a language. The best training is to read chemistry journals and to try to understand the chemistry and the reasons for each article. Actually, many articles make no sense at all. People often take expensive starting materials and convert them into readily available, inexpensive products. Instead of just scanning articles, students may also ask themselves how to prepare certain compounds or how to improve a published synthesis. And most importantly, you should understand the reaction mechanisms and be able to reproduce them by hand on a sheet of paper. Moving electrons around is a critical skill for chemists. In a multi-step synthesis, the highest yielding steps should be at the end of the synthesis because late-stage intermediates are the most expensive. Low yield steps can only be afforded early in the synthesis. And convergent strategies tend to give higher overall yields than linear strategies. In a linear strategy, the initial fragments undergo a large number of chemical transformations, while in a convergent strategy, each fragment undergoes fewer transformations and losses. So what is a good synthesis? As mentioned above, this depends on the scale and purpose of a synthesis. When conducting a multi-step synthesis on a large scale, there are more limitations to what can be done than in a laboratory scale synthesis. Low or high temperature reactions or high pressure can be difficult to realize in a large reactor. And because time is money, industrial syntheses cannot afford a high dilution and must be run at the highest concentration possible. The most reactive reagent has to be added slowly while the reaction proceeds to avoid the accumulation of unreacted reagents. Mixing all reagents on a large scale will usually cause a thermal explosion. Many reactions published by academic groups consist in mixing everything in a hermetically closed pressure vial and heating overnight. Such reactions cannot be scaled up. All catalysts, reagents, starting materials, and solvents should be as inexpensive as possible, and the waste should be easy to dispose of, for instance by burning. Ideally, reagents and intermediates should be stable, perhaps even to water and air, and only slightly toxic or corrosive. Reagents must, of course, have a certain reactivity, and there is no such thing as a non-toxic compound. Then, good syntheses are short, give high yields, and are designed to simplify the isolation and purification of products. Only distillation and crystallization are allowed, not chromatography. Some bond-forming reactions have been optimized a lot and tend to give high yields, while others are more difficult and give lower yields. This is a rough guideline only, with many exceptions, but it is good practice to place highly optimized reactions at the end of a synthesis. In other words, the first retrosynthetic steps should be reactions that are most likely to give a high yield. Acylations, for instance of amines by activated carboxylic acids, are the most optimized reactions because in solid phase peptide synthesis, each step must proceed with almost quantitative yield. Some heteroatom alkylations also work well, the worst being the formation of ethers from alkoxides and alkyl halides. Carbon-carbon bond-forming reactions usually give lower yields than acylations or heteroatom alkylations. Ketones can be obtained from carboxylic acids and arenes, for instance by Friedel-Crafts acylation or by addition of polar organometallics to nitriles or esters. Aldol condensations and Wittig-type reactions yield olefins, while some few reactions can yield alkanes directly. The latter are better prepared by hydrogenation of alkenes or alkynes, or by reduction of ketones or aldehydes. Another rough guideline to reaction yields is that reactions which involve a change in the oxidation stage of carbon tend to be more difficult and give lower yields than transformations without such redox processes. For instance, the interconversion of carboxylic acid derivatives, for example, nitriles into amides or acids, proceeds in high yield. Similarly, ketones readily form acetals or enamines, again in high yield. To convert carboxylic acids into ketones, however, is more tricky, and yields tend to be lower. I've also discussed this issue in my first video about carbon dioxide. Another important consideration in retrosynthetic analysis is the reversibility of reactions. Some transformations are reversible, for instance, monic reactions, aldol additions, or the formation of hemiacetals from alcohols and ketones. Such reactions cannot be used to make strained bonds. For example, the zinc enolate shown at the right side of this equation did not cyclize to a cyclopropanol, but was formed by ring cleavage of a cyclopropanol. The equilibrium here was on the side of the open-chain ketone, and reaction with benzaldehyde gave the expected aldol addition product. Thus, cyclopropanols cannot be prepared by intramolecular aldol addition. Gamma haloenolates, however, do cyclize to cyclopropanes because CC bond formation is irreversible in this case. Heating chlorobutyronitrile with solid sodium hydroxide yielded, after hydrolysis, an acceptable yield of cyclopropane carboxylic acid. Interestingly, because of the low solubility of sodium hydroxide in chlorobutyronitrile, no hydroxybutyric acid was formed. Okay, let's have a look at some specific examples. We'll start with nicotine, the alkaloid of the tobacco plant. If we had to manufacture enantiomerically pure nicotine on a large scale, for instance as insecticide or to fill up vaping devices, the first step would be to compare the prices of potential starting materials. The least expensive would be 3-picoline, but nicotinic acid derivatives are inexpensive too, because these are vitamins and are being produced on a huge scale. More expensive are proline and 3-halopyridines. Because carbon-nitrogen bonds are easy to make, a retrosynthetic analysis of nicotine should begin with cleaving each of these 3 bonds. Demethylation would not be helpful because it does not simplify the structure. Demethylated nicotine is as synthetically challenging as nicotine. Cleavage of the NCH2 bond, however, yields an aldehyde, which might be accessible by Michael addition of an aminomethylpyridine to a acrolein. This approach does not look promising, however, because it would require an enantioselective Michael addition to a acrolein. Few examples of such reactions have been reported, and acrolein has 2 electrophilic sites and is difficult to handle. This Michael addition would also require a strong base because 3-picolines are not particularly acidic. A third strategy would be retrosynthetic cleavage of the benzylic carbon-nitrogen bond. This yields a ketone, accessible from nicotinic esters or 3-cyanopyridine. We may also consider preparing nicotine from proline. One strategy would be to convert the carboxyl group of proline into a 3-pyridyl group. I could not find any reported example of such a transformation, but it would probably require several steps. I've sketched here one possibility. The overall yield of this synthesis is likely to be low, even if every step works as expected, and many things can go wrong. The large number of steps would also increase the costs. More realistic is perhaps the alpha arylation of proline with 3-bromopyridine. A number of similar reactions have been published. The main challenge would be to achieve an enantioselective transformation, yielding the right enantiomer, again, an unrealistic goal. So let's again have a look at the retrosynthetic cleavage of the benzylic carbon-nitrogen bond. To obtain enantiomerically pure nicotine, the intermediate ketone would have to be aminated enantioselectively, and many examples of such reductive aminations have been published. Then, to prepare this ketone, we could introduce an alkoxycarbonyl group as electron withdrawing auxiliary, and the resulting ketoester could then be prepared by Claisen condensation of a nicotinic ester with some gamma-aminobutyric acid derivative. The enolate of NMP could be a practical option because NMP is an inexpensive solvent manufactured on a large scale. Other gamma-substituted butyric acid derivatives are also readily available. This synthetic strategy has recently been realized successfully. Claisen condensation of methyl nicotinate with NMP gave the acylated lactam, which was hydrolyzed and decarboxylated in high yield. Enantioselective hydrogenation gave nicotine with 88% enantiomeric excess, but this might still be optimized further. Alternatively, the optical purity may be enhanced by recrystallization of the hydrochloride or some other salt. In this patent, the authors developed an enzymatic reduction of the intermediate enamine and obtained nicotine in 83% yield, with an enantiomeric excess of 99.4%. Importantly, the enzymatic reduction could be carried out at a relatively high concentration, which is important for the final production costs. Let me show you another example, the new insecticide, chlorantraniliprole. Here, the most obvious first retrosynthetic step would be cleavage of the central amide bond. This yields an aniline and a pyrazole carboxylic acid, which should be easy to combine to the final product. One potential approach to the pyrazole could be arylation with a 2-halopyridine, as sketched here. Pyridines are electron-deficient heteroarenes that readily undergo aromatic nucleophilic substitutions. But electrophilic arylation of the starting pyrazole would probably yield a mixture of two isomers. A better approach would be to use a pyridyl hydrazine for the preparation of the pyrazole, because in the pyridyl hydrazine, both nitrogen atoms would have a different nucleophilicity, which should improve the regioselectivity of a pyrazole synthesis. Alternatively, a pyrazolidinone could be prepared from hydrazine and a fumarate. Here, again, both nitrogen atoms would have a different nucleophilicity, which should enable the selective arylation of the more nucleophilic site. One literature synthesis is shown here. Dichloropyridine was first converted into a hydrazine and then cyclized with diethyl malleate. Deoxybromination, dehydrogenation with persulfate, and saponification then gave the required pyrazole carboxylic acid. For the anthranylic amide, a larger number of potential starting materials can be considered. Nitrotoluene, metatoluic acid, and toluidine are the least expensive. Starting with nitrotoluene, one potential strategy could be a modified von Richter reaction. It is known that nitrobenzenes react with cyanide to benzoic acids. An intermediate benzamide is oxidized by the orthonitroso group to yield nitrogen and the ortho-unsubstituted benzoic acid. In the presence of an oxidant or a reducing agent, maybe this deamination can be prevented to yield an orthonitro or orthoamino benzonitrile. This has certainly been attempted already, but should be followed up further. Another approach is the orthocarboxylation of toluidine. Anilines can be carboxylated, but less readily than phenols. In two recent examples, carbon monoxide was used instead of carbon dioxide. This strategy is likely to succeed, and the precise overall costs will determine if this approach is realistic or not. It may also be possible to methylate anthranylic acid with a method described in organic syntheses. Again, this strategy is likely to work, and the overall yields and costs will decide if this approach makes sense. One recently patented synthesis starts with the nitration of metatoluic acid. Unexpectedly, this nitration gives the orthonitrotoluic acid as the main product. This is a surprise because benzoic acid is nitrated at the meta position, and if the methyl group had a strong impact on the regioselectivity, nitration should have occurred para to the carboxyl group. But yes, strange things happen from time to time. The yield of this nitration was only 45%, but as I said before, this is no tragedy because it is the first step of the synthesis. A further challenging building block is 2,3-dichloropyridine. The most attractive starting materials would be 2-chloropyridine and 2,6-dichloropyridine, manufactured on a large scale by direct gas phase chlorination of pyridine. Valerolactam and niacin are also potential starting materials, but probably more expensive. One persistent problem marring synthesis design is that bulk prices of reagents are not fixed and available, but must be negotiated each time. Therefore, cost calculations are always rough approximations only, also because of the uncertainty of purification procedures and yields. One straightforward synthesis of dichloropyridine starts with the Hofmann degradation of niacin, followed by oxidative chlorination and a Sandmeyer chlorination. The advantages are that each step mainly yields one isomer, and that most reagents are inexpensive. Still, the synthesis requires 3 steps, and the disposal of copper waste can be costly. In one newer patent, the authors claimed that trichloropyridine can be hydrogenated selectively to 2,3-dichloropyridine, with yields up to 85%. In order to achieve such yields, the hydrogenation must be monitored and stopped at the right time to prevent further dechlorinations. Another reported synthesis is the 3-fold chlorination of valerolactam, followed by dehydrochlorination and deoxychlorination with phosphorochloride or phosgene. The main issues here are the price of valerolactam and the phosphorus waste if the deoxychlorination requires phosphorochloride. There is a strong demand for lower-priced 2,3-dichloropyridine, and people are getting really creative. In this example, the pyridine ring was formed by a Vilsmeier reaction of an N-vinyl chloroacetamide. One problem here could be the handling of acetaldehyde, an extremely flammable compound which requires special equipment when dealt with on a large scale. Finally, the best synthesis would be the direct regioselective chlorination of 2-chloropyridine. One recent patent claimed this to be possible with a trichloroguanidine and iron trichloride as chlorinating reagents. Usually, however, chlorination of 2-chloropyridine yields 2,6-dichloropyridine. Let me show you one last short example, the title ketone. This compound does not contain any acyl groups or heteroatom carbon bonds other than the ketone. Therefore, the retrosynthetic steps must be ketone-forming reactions. For instance, the alpha-alkylation of ketones, Claisen condensations, and similar reactions. For example, it might be possible to alkylate cyclohexanone with diiodobutane. I've chosen an alkyl iodide because these are soft and well-suited for alkylations at carbon. One potential side reaction is alkylation at oxygen, but with alkyl iodides, we minimize this risk. Many variations of such enolate alkylations have been reported, and successful conditions can probably be found. Moreover, the starting materials and related compounds are readily available. Instead of just cleaving bonds, we may also add auxiliary functional groups during a retrosynthetic analysis. For example, the target product should be accessible by decarboxylation of a ketoester, available by Dieckmann cyclization. The required diester can be prepared by alkylation of methyl cyclopentane carboxylate, which in turn is made from chlorocyclohexanone by Favorsky ring contraction. This synthesis is, however, too long if compared to the direct alkylation of cyclohexanone. The target ketone may also be accessible by hydrogenation of an enone, which could be prepared by intramolecular aldol condensation. The required aldehyde can perhaps be made by Michael addition of acetylcyclopentane to acrolein, but this reaction can yield many other products and is therefore unlikely to proceed cleanly. So, from this analysis, I would consider the direct 2-fold alkylation of cyclohexanone as the best approach. Retrosynthesis is pattern recognition, however, and our target is a spiro 4,5-decane and a tertiary alkyl ketone. These two structural features should trigger pinocol rearrangement in the chemist's mind. In fact, compounds like the target ketone are formed when the symmetric pinocol dimerization products of ketones are treated with acids. Thus, it should be possible to prepare our target ketone in 2 steps from cyclopentanone without the need of alkyl iodides, strong bases, anhydrous conditions, or low temperatures. This synthesis has been realized, but yields and selectivity were only low. Thus, some further optimization is required. Pinocol dimerizations can also be achieved with zinc and trimethylchlorosilane, and under certain conditions, the McMurray coupling of ketones yields diols instead of olefins. Thus, it should be possible to increase the yield of diol. Then we would have to calculate the costs of each approach to see which one is the least expensive. Okay, I'll stop here. I hope that with these examples, you've got a better understanding of what matters in synthesis design and how to proceed. As discussed in my previous video about project selection, new active ingredients like chlorantraniliprole are a fertile area for new, relevant research projects. The synthesis of chlorantraniliprole is challenging indeed and poses several interesting chemical questions. Thanks for watching, and see you next time.